Let me just go ahead and get started.
I think maybe 1 minute just to allow people to get in from the Zoom link, but
Okay.
yeah, should be good anytime.
Okay. Cool. Well, then I'll go ahead and get started. Good evening, everybody. Welcome to the EERI Chico State Chapters, Chico State Student Chapters hosting of the Friedman Family Visit. Today, I'm joined by our chapter and Megan Vandervoort, as our SLC moderator for the night. Tonight, we have the honor of hosting a very accomplished structural engineer, David Friedman, who is certified as a structural engineer with over 40 years of experience, and is not only the chair of the board of directors, but also the president and CEO of Farrell Elsesser Engineers. With a specialty in seismic engineering and retrofitting of existing structures, David has solved numerous structural and earthquake engineering challenges during his career. David is going to share with us a few of his projects that he has worked on, giving us his insight and industry experience. With all that being said, we are honored to introduce you, David.
Thank you very much. I wish I was there in person. I love meeting students. I love being on campuses, and I guess after post-COVID, I'll have to invite myself up to campus to see you all again. You know, I've done a lot of these visiting professional presentations with the ERI, and I've for this year, not just the getting ready for the Zoom, but I've given a lot of thought to, so here I am at the end of my career. What is it that I think would be interesting for students and people at the beginning of their careers? And so really there's only really two things that you need to know about me. One is I have loved my profession. I have loved my career. It's the projects, it's the learning curve, it's the people you meet, it's the challenges of the project. In retrospect, I couldn't be happier. And earthquakes have framed my career in a lot of ways, and I give a lot of credit to that okay, this will not let me advance the slide. Is there something I am doing wrong in not being able to advance the slides?
Maybe at the bottom, are you able to click that right arrow down there at the bottom?
Oh, maybe, yeah, I'll say,
there we go.
Thank you. So, you know, this is kind of a public service advertisement for EERI, but I got involved with EERI maybe 30 years ago, just as a volunteer. Became a member and started attending annual meetings, and then gradually got more and more involved. And, you know, for those of you who don't know EERI, it's a global earthquake engineering, you know, technical organization. Its mission is really to advance the science and practice of earthquake engineering and reduce earthquake risk around the world. The best part of EERI is who makes it up, you know, and, you know, whatever discipline is our specialty, there is something about rubbing elbows and getting to meet people who come at earthquake engineering from different perspectives beyond your own, you know, and you see here that, you know, who are the members. And I found it particularly interesting meeting and getting to know and working with social scientists, people who are working on disaster planning and disaster recovery and kind of the human side of what happens after a natural disaster. Particularly the Learning from Earthquake program is really the program that kind of knocked my engineering blinders off and made me really understand that an earthquake doesn't just affect the buildings that we design, but it affects whole neighborhoods, whole cities, and is a regional disaster. There are many activities within EERI. For student members, for after graduation, there are lots of ways of getting involved. There are regional chapters that really are very interesting to get involved with. I highly recommend you. I mean, I'm preaching to some of the already converted who are EERI student chapter members, but all of you, even if your discipline isn't necessarily earthquake engineering, I really think there's something about this organization that will set you on a learning path through your careers. So my career, and I've created this timeline that I'm going to keep coming back to. I've only had 3 jobs in my entire careers: 2 years, 3 years, and 40 years. I retired officially end of last year. And my wife said to me that, you know, either my tenure of 40 years was either due to stamina or a lack of imagination. But I think it had a large part to do with, you know, I just was on the kind of path that I wanted. You know, I ended up being the CEO of the company. I started my career having no interest whatsoever in necessarily being a practice leader, but I found my way, you know, involved in management, and actually do not begrudge that part of my learning curve, you know, even though it did to some degree take me away from doing projects. I mentioned earthquakes, and, you know, kind of I have added to my timeline the earthquakes, and not just the earthquakes that happened during this time period, but each one of them in some way or another affected my career. Affected my career relative to, I was on an EERI reconnaissance team, or there were significant code changes that happened because of those earthquakes. You know, the first one is the Great Earthquake of San Francisco. No, I wasn't alive here, but little did I know that the replacement building was going to be one of the big projects of my career. You know, what's very interesting about this earthquake was not just the ground shaking that lasted 63 seconds, but the fires that happened afterwards, adding to most of the destruction of the city. 1971, I was still in school, but this was the San Fernando Sylmar earthquake. What was important about this earthquake is photographed here is the Olive View Hospital. It was after this earthquake that we changed our codes specifically for essential services buildings, that we knew that hospitals needed to have a better performance than shown here. I think also this was when we really woke up to the need for ductility in our designs. There was no transverse reinforcing in those columns. The Llama Prieta earthquake. In a way, this earthquake was the bane of my existence professionally, because the earthquake was really not a big earthquake. It was maybe bigger for Santa Cruz, but not for San Francisco. Some celebrated damage, but it was also only 8 seconds of strong ground motion. If it had been twice as long, it would have been tenfold the amount of damage. But so many clients, so many people I run into, building owners, say, my building survived the big one. And I went, really? This building was around in 1906? They say, no, 1989. So kind of getting people to understand that that really was not a big earthquake has been kind of really difficult. Northridge, 1994, I was in practice at this point. You know, this was a, you know, there were maybe 7 or 8 parking structures that fell over, and it was just because of the aspect ratio of the diaphragms, not necessarily, you know, that it wasn't a strength issue or a shear resistance issue. Kobe, Japan, I was on the reconnaissance team for. This was a really, I was going to say groundbreaking, but no pun intended. But I think one of the things we all learned from this earthquake, and as evidenced by this viaduct structure, that those concrete columns are 24 feet in diameter, and it told us a lot about brute force approach to earthquake resistance. It doesn't work. Again, you need ductility in your design. Banda Aceh earthquake in 2004, we really didn't start talking about tsunamis until this earthquake. And this was the real story of this earthquake, was the massive, massive tsunami that happened afterwards. Wenchuan, China, I was on this reconnaissance team as well. I think there are lots of lessons of this earthquake. A lot of it was the earthquake-induced landslides that happened in the region. In some cases, so big that it wiped out entire cities. Haiti, 2010. The tragedy of this earthquake wasn't, maybe the learnings weren't the code changes, but it was more the devastation that happened to this country, where they measured the amount of damage as 2.5 times the gross national product. And no wonder they've struggled to recover from this earthquake. Christchurch is very interesting, and a more contemporary earthquake in a country that has great codes and great engineers. There were actually 2 earthquakes within 4 months of each other. The second one that was actually lesser magnitude, but was a shallow earthquake underneath the city of Christchurch and had totally devastating impact. And then Tohoku, Japan, this was another, large earthquake, large magnitude earthquake, and of course the story of the tsunami. But one of the things that was really interesting about this earthquake was, we talk about earthquake magnitude, and people get fixated on what the magnitude is, but it's also the duration of strong ground motion. And in the case of the Tohoku earthquake, the strong ground motion lasted 2.5 minutes. So that's why there was so much non-structural damage far away in Tokyo, Japan. Some lessons learned about in my engineering career. My favorite definition of structural engineering is this. Structural engineering is the art of molding materials we do not entirely understand into shapes we cannot precisely analyze, so as to withstand forces we cannot really assess in such a way that the community at large has no reason to suspect the extent of our ignorance. Now, we're really not ignorant. We're really, we try and be quite educated and quite smart. But what this does talk about is there's a lot of uncertainty that we have no control over. I mentioned the earthquakes, the magnitude, the ground motion, the content, vibration content. But we also have to acknowledge that as we talk to people about what we do, that there's a lot of things that we have to talk about in probabilistic terms. And once we talk in probabilistic terms, we lose people very quickly. And so we have to understand kind of what it is we're trying to convey to people. Some of the issues that we face as structural engineers is the code, and the code's constantly changing. And I mentioned we chase earthquakes around the world, and we learn from them, and we change the codes. One thing that has never changed about the code is that, at least as far as the seismic provisions in the code, is that it's a minimum standard. And what does that mean? Minimum standard is for life safety. It means that we design buildings so people can safely get out of the building. It doesn't mean you can get back in the building. So in this little diagram, a code conforming building design would be the moderate disruption building. We expect damage to happen, but a lot of people don't expect that that's what we're delivering when we say where we're designing. They expect this, but this operational building is a high performance building. You know, we can design these. We can design minor disruption or limiting damage, but this is really one of the things that we have to understand as we use the code. We can't use it as a cookbook. We have to understand what it's delivering in the way of performance and make that clear to our clients so they understand what it is. The code also anticipates that we're designing regular shaped buildings, really doesn't quite as much envision the irregular buildings that architects like to design, like this, or like this. This is in Copenhagen, Denmark. Some people think it's an after earthquake photograph, but that's the design. But our challenge as engineers, as practicing engineers, is to put regular systems, regular structures to make these buildings stand up. You'll see as when I talk about a couple of projects, engineers of record, only promise their buildings are safe once the buildings are completed. But a large part of my project history was in seismic retrofits to historic buildings. And some of those buildings were in construction for 2.5 years. Generally, the engineers of record are not responsible for stability during the course of construction. But in some cases, we had to be concerned about the stability during construction because of how long it was going to take. And I'll show you some of that in the San Francisco City Hall project. Sustainability has become a big buzzword in design, in architecture. Usually sustainability refers to energy and energy use, energy design. But they kind of forgot about seismic sustainability along the way. And now seismic sustainability has given way to talking about resilience. How long does it take for a building to recover or a community to recover? And these have been some of the areas that later in my career that I've become more and more impassioned about and an advocate for. The other thing I want to impart to you is, engineers get a bad rap, maybe deserved, but they're considered not to be particularly articulate and literate. I think we actually are, and we can be, but we do have to acknowledge that we're in a tough position because we need to be able to explain what we do to a lay audience in a way that they can understand it. And there's a number of times where you're writing a report and you have to understand who your audience is. So kind of spelling and writing and speaking quality does count in professional practice. So projects. So I've done a lot of projects in my career. I'm really going to talk to you about 2.5. The San Francisco City Hall, this first project, which really consumed about 10 years of my career, and then the seismic safety corrections of California Memorial Stadium. And again, a lot of these earthquakes up here and code changes and things really impacted a lot of these projects. The first project I'm going to talk about is the base isolation retrofit of San Francisco City Hall. So I'm not going to assume that you all know exactly what base isolation is. So I'm going to give you a brief primer on what it is. So what are base isolators? They're really 3 kinds. Bearings bearings were used on bridges for a long time, but they really hadn't been used in an aseismic capacity. One of the most common types is a high damping rubber bearing pictured on the left. There's some aberration of it where the same kind of high damping rubber bearing with a lead core placed in the center of it that allows for more energy dissipation. And then there's the friction pendulum, kind of a different kind of concept. But all of these are vertically very stiff and laterally flexible, because this is where the energy of the earthquake gets dissipated. Order of magnitude of size is they're about, the high damping rubber can be 20 to 24 inches tall, 30 to 36 inches in diameter. The friction pendulums can be anywhere from 3 feet to 6 feet square, usually. We're agnostic as to what kinds we prefer. There are two basic reasons why you base isolate a building. The first one is pictured here. Most fixed base buildings, and a fixed base building is anything other than a base isolated building, where the building is going to withstand interstory drift. From floor to floor, the deflection of the building is going to cause it to drift, and that drift is what causes damage in the building. When you base isolate the building, most of that deformation is happening in the isolators. And so you have to design a building for a lot less interstory drift, because the whole building is moving more monotonically. The other reason that we base isolate a building is because of the period shift. So again, most fixed base buildings is in this lime green zone. A lot of the buildings we design are, in the half a second to 1 second fundamental period of vibration range, and that puts you right at the peak of the response spectrum. But the base isolators have a fundamental period of vibration of between 2.5 and 3 seconds. So if you read across, with a fixed base building, you get something like a 1.1 G lateral acceleration, but in a base isolated building, you get about 0.2 G. So you can see the benefit of the period reduction and the spectral acceleration on the building. So that's essentially why we do it. We started doing base isolation retrofits. The very first one was a city and county building in Salt Lake City, which was the precursor to the next one we did, which was San Francisco City Hall. This is San Francisco City Hall, the building that was built in 1915 after the destruction of the building that I showed you in 1906. This shows again the damage where most of the brick cladding had been shaken free of the building. This shows basically what we did in the retrofit of the building, and all I'm really going to talk to you about is at the base is the base isolators and how we got them in. It involved putting in new foundation systems, creating this isolation plane, cutting the columns, tucking in the isolators. But then we also had some strengthening to do in the light courts on each side of the rotunda and the drum and the dome of the building. You can see in red some of the steel transfer systems and strengthening of the drum that supports the dome of the building. This was actually the main reason why we base isolated the building, because had we done a fixed base, we would have actually had to have strengthened or rebuilt the entire dome, the inner dome and the outer dome, and that would have been cost prohibitive. So remember, we were doing this in the late 80s, early 1990s, and we were trying to explain to a client what it is we were doing. So what you're seeing here is the fixed base model retrofitted of the building, and on the right, the base isolated building. This is our 3D model of the building, and we're running a real earthquake time history. I'm going to show this again because this is frankly the best part of my talk. So as the earthquake gets going, keep your eyes on the dome on the left, and you see how much that is moving. And you look at the corner pediments of the building, the entry pediments of the building, and how much deformation is happening. Then go over to the base isolated building, and you see that building moving more monolithically. You know, that we amplified this, but not amplified it so much that you can see there is deformation happening in the in the drum and the dome. But that's how we controlled a lot of the damage to the building. So this was priceless in terms of being able to show this to the client, and get them to understand why we were doing this. The main trick here was, so how do you get the isolators in? And a lot of our detailing had to be around what the sequence of construction was. I mentioned to you that we certainly weren't making the building a lot stronger. In fact, during the course of demolition at the first floor, we were taking out a lot of brick and terracotta walls. So we were actually making the building weaker. So we designed a rather large temporary bracing, which was all around the building. And we felt we needed to design it just because we would design it to a different level than the contractor would have probably installed some rod bracing, which wouldn't have worked. So what you're seeing in this photograph is we've done a lot of excavation around the existing footings, put reinforcing in, scraped off the concrete fireproofing to expose the lead paint on the steel columns. Here you're beginning to see a number of things happening. You can see where we've scraped off the paint. They've installed these very, very stiff steel beams that clamp and sandwich the column. They're supported on spreader beams here, and then these are the hydraulic jacks. You can see, and this is the apparatus getting started. We, in each of the 4 quadrants of the building, we limited ourselves to only doing 3 columns at a time. Once this apparatus was in place and clamped, there was a load bypass, meaning the load coming down to the column was, by the stiffness in these girders, was being transferred here, so we could activate these jacks and infinitesimally jack this up to release any load that was coming in the column. Then we come in and cut the column here. Then we eliminated the old foundation that was there, poured a new foundation, put in setting plates for the new isolators. These pictured here are the columns, the 5 columns that support the rotunda. So each of these had 4 isolators in them. Over here on the left, you can see an isolator has been installed. You can see the beginning of what we call the cruciform steel floor framing, vertically very stiff because they're only 14-inch deep girders, where we use column sections for the floor because we're fighting for every inch here. And then this shows the actually a whole row of columns ready to go. The isolators are in, the cruciforms, more floor framing would be attached to these. Interesting here is each isolator had a locking plate. There are 538 isolators in San Francisco City Hall. I may have that number wrong, but these locking plates were important because until we had all the isolators in, until we had the floor completed and the concrete diaphragm in, and in fact, the rest of the strengthening of the superstructure of the building, we didn't want the isolators activated. So only after the project was done did they have to go into the crawl space and remove all of these locking plates. And this is more of the floor framing in. Again, that isolator plane was competing for a lot of space. We also had to be able to come in and inspect and remove every isolator. So there are access ports located throughout the building to be able to inspect the isolators after an earthquake, and they're required by code to be tested, or at least a couple of the isolators tested at every 5-year increment. I'm going to show you very quickly one other project. And the story here, this was a different delivery system. This was what we call design build. So there was an architect and an engineer and a contractor design team involved in the project before us. And then it was handed over to the engineers of record. And basically that is to find some efficiencies in the design of the building. This building, this is a finish shot. This was one of the most difficult projects we worked on from a site perspective and architectural perspective, because they came up with a very serpentine building. They had already decided that this building would be base isolated. They already decided and procured the friction pendulums for this, but they hadn't solved one issue, which was the overturning on the isolators. And because of the small aspect ratio, this was not a heavy building, there was a net uplift on the isolators. The isolators, again, these were what we call the triple friction pendulums. Their uplift restraint were these little strapping devices. And for the excursions that these isolators were going to undergo, those strapping devices weren't going to survive, let alone be there for any uplift resistance. So we had to solve this problem. And we had to be really more mechanical engineers than structural engineers. One of our engineers had an idea of how to make a restraint. Over a weekend, he took his son's rollerblades apart and came up with this concept. That concept turned into a mechanical system of being able to handle the three-dimensional motion and provide a clamping so that the uplift could be restrained. It wasn't done right adjacent to, it wasn't done within the isolator, it was done adjacent, and which is why we have very stiff kind of load transfer elements here, but this was the actual uplift restraint. Again, you can see even in the friction pendulums, we had these same locking constraints in the building so that the building was in place, or it was locked in until the building was completed. We had to test these down at UC San Diego. This is actually the finish of the structure. I kind of thought it looked like a piece of art and kind of wish they had just stopped there. But again, look at the serpentine nature of that building. It was really a but when we started this project, as the engineers of record, there was a problem we didn't know we were going to have to solve, but we did. California Memorial Stadium. This was another 10-year spanning project in my career. There were actually two projects. One was a high performance student athlete building, a crescent-shaped building in front of the building. That was done first to decant the building. The building was a historic structure, mainly the wall, perimeter wall. The building was built in 1922, designed by John Galen Howard, a famous architect in Northern California. The building was built in 9 months. I love these old photos showing the mules carting the soil out. The building was built for $1 million. And this project took 22 months and maybe about 3 years to design. It wasn't helped by the fact that we were delayed by a large amount of litigation from the city and the neighborhood association. This shows the part of the West Bowl, which was a non-ductile concrete project structure. Many of you know of the seismic activity in the Bay Area. We were dealing with the active Hayward fault. We knew that the fault was there. We knew it ran under the stadium. We didn't know exactly where it was. We were forced to do a fair amount of trenching, particularly for that precursor project, to make sure that we weren't getting faulting activity under a new building, because you're not allowed to build a new building on top of an active fault. We knew that the fault was somewhere in these areas. In green were the trenches that were dug. These trenches were the result of the litigation to basically prove that the fault was where we thought it was and not where we thought it wasn't. And luckily, this trench showed the fault, and the geotechnical engineers loved getting in, and they were very skilled at mapping the soils. And when they saw this, this clear delineation between soil types, that was an indication of the zone of where the fault was. So approximately that red line is where the fault is, running almost north to south, a little bit diagonally. The issue with the fault is not the ground shaking. We know that's going to be, we're in near fault zone, and it's going to be intense ground shaking, but the real issue was fault rupture and displacement. So the geotechnical engineers told us that the displacement would be as much as 6 feet horizontally and up to 3 feet vertically. We did a lot of study with the help of some professors, the UC Berkeley campus, where they had viewed fault rupture in many places. Here was an example of vertical fault rupture of order of magnitude of 6 feet. Kind of interesting to see the building didn't even have glass breakage in the background. This was a building in Taiwan. There were actually 2 buildings. The first one collapsed, and really right along this plane is where the fault was rupturing. The issue with this building was that it was pile supported. The piles locked the foundation well into the ground. That told us something. Even nature tries to tell us something. When you consider the way the fault rupture went up the tree trunk, think about the root system as locking the tree into that structure. There were some good examples of little bunker-like buildings that had a ribbed or mat-like slab that was very level, and all that happened to this little building was that it rotated and tilted a little bit. So that gave us our first clue as to kind of what, before we started modeling anything, we came up with a concept. And the concept was that we were going to create these fault rupture blocks. The block would be very stiff, would have shear walls in it, but it would be jointed. on each side. But that joint, different from a normal seismic joint, that joint would run completely through the foundation. It would sit on a mat foundation that would be very rigid, and it would be level. And we would put it on a couple of layers of plastic sheeting just to help it a little bit, because the behavior that we were looking for was when the fault ruptured, we would want it to rotate or tilt a little bit. After all, what we were after, what the code was after, was life safety. We weren't trying to do something. Everyone expected us to base isolate this building, but in fact, we used really basic statics on this. The big issue, so we had one in the north and in the south. We had a fault rupture block. It was informed by the geotechs who gave us not only where the highest probability of the fault rupture was, but what angle it was going to act at. So then, we started more of our modeling, and we also took into account different parametric studies of saying, not only what if the fault ruptured here, what if it happened over here? In this case was a study where we said it would be a series of ruptures in this zone. And maybe the geotechs were wrong, and maybe it would fall outside of the zone that they predicted. So that did lead us to, in the green zone, deciding to at least put in a heavier mat slab foundation in that area. We used a finite element model to study the behavior of this. We used Abacus to do this kind of finite mesh analysis. We also did a physical model. The physical model was the suggestion of the Seismic Review Committee at Berkeley. We thought it was, a not so high-tech suggestion, but they said, we said, sure, we'll do a physical model. How do you suggest we do that? And they said, well, you're the engineers of record, you figure it out. But we actually did figure out a really fun, crude physical model, and we compared it somewhat to what our analytical models, and it was order of magnitude. It gave us a similar kind of results. Again, we're trying to communicate what we're trying to do to a client, a lay audience. So we made this kind of Google Earth zoom in. Sorry, let me start it again. There's going to be 3 views. It's really the third view that really is demonstrating the behaviors we were looking for. But you'll see it's a little pixelated at first, but you'll see that we mimic a little bit of shaking, and then in the stadium bowl you'll see a little rupture. But this is a slightly better view where you'll see the fault rupturing in the stadium, and that block rotating and tilting a little bit. This is the better view. Again, we don't expect it to be, particularly dramatic. It will be somewhat, the people sitting in that section, should there be an earthquake on one of the 5 fall afternoons where there's an earthquake, they probably will be more preoccupied with the ground shaking than that translation of what's happening to the bowl they're sitting in. But we spent a lot of time on that fault rupture solution, because we said the west bowl of the stadium that had also this big press box lacing through it, and this press box basically runs from end zone to end zone. It's 330 feet long. Its lateral span is only 100 I mean, its vertical span is only 110 feet, but its lateral span is between the two pairs of concrete cores. And then there was the stadium bowl around it. But we were pretty complacent. I wouldn't call us smug, but we've had retrofitted lots of non-ductile concrete structures before, and we thought, we can do this. This will be easy. We were quite wrong. And I take this because, as an example to you, just because you don't always get too lockset in what your solution is going to be. So that this is a cross section through a transverse section through a radial wall of the stadium and one of those core walls. These transverse walls happen more frequently than the core towers do. But we ran this triangulated element is a very stiff element, and this inverted pendulum is rather flexible. So what did we learn? We learned that we were getting, because of the axial stiffness of the bowl slab and the raker beams, that we were getting buckling in this element here. We're also getting yielding of the core piers in these elements there. And well, we said that's not good. So the first thing we did is let's put in a slider here. Let's release that slab and raker beam, so we did not get the kind of rupture, and we put in a little ductility into these core walls, but we were still getting yielding of the core piers. So we said, well, that's not good. So maybe we need a little bit more energy dissipation in the system. So we decided to put a very large opening. It's the first time I'd ever gone to an architect and asked for an opening in a shear wall. Usually it's the other way around. But this way we thought we could get enough ductility in the system, but it still didn't work very well. So finally we said, why are we fighting it? Why don't we let the two buildings, because they were really two buildings, why don't we separate them, let them behave differently? And that was kind of an aha moment, where we thought that was the right thing to do. But then we had to give it a little bit more strength. So we turned those core walls into, we vertically post tensioned them, and they became rocking piers for the energy dissipation. We did put a collar around the slabs to make sure that we controlled it. But then we had one more thing up our sleeve. We decided to put in viscous dampers to help control the differential motion between the two buildings. So whereas everyone expected us to throw in the buzzers and whistles into the fault rupture issue, it was really here where we used every engineering trick we possibly could. We again used a finite element study the nonlinear behavior of these, and again we did a little animation to show the client. This doesn't really scale very well, but you basically see how much the core and the press box is moving relative to the relatively stiff bowl structure. Always construction is kind of the fun part, though you always run into problems, but you also think about construction process as you go. I love showing this picture of the radial shear walls in the building to people on the East Coast, because they're just awestruck by how much reinforcing steel goes into those coupling beams. And then the details of those rocking piers. The vertical tensioning went into these sleeves. Here's a picture of the sleeves here. And then all of these number 11 bars are meant to resist a thrust. And this is the mat footing. The mat footing is, I believe, 7 feet thick. This is where a lot of the transfer is happening. This is where the steel press box is connecting to the core walls. We have a 7-inch diameter, 100 KSI pin, 4 of them at each core. And then, I don't know if I have a picture of the damper. Maybe I do coming up. This was our Revit model of the stadium with the bowl slab turned off. This was after demolition of everything on the inside of the historic wall. This shows the 4 tower cranes and construction beginning on the west bowl. The tricky thing about this project construction-wise is every piece of material out, every piece of material in, all had to come in through the North Memorial Arch. And in fact, we had a contest one day. This was one of the largest foundation pours of who could take a photo of the most concrete trucks. And our person who was permanently on site took the photo. This shows the West Bowl slab framework going in. Once we got that in, we were able to take out the 2 eastern tower cranes. And then they, this is actually shows the south fault rupture block. So you see the joints, and the joints are 12-inch joints. Again, the joints that go all the way through the foundation. And this is the other side of the joint. You might notice that the grid of the stadium, the radial grid, is different than the angle of the joint. The architects were rather upset with us when we told them that we were going to put the joints where they needed to be by where nature was likely to rupture. And they fought us tooth and nail on it until we explained if we put the joint on the grid, the joint would be twice as large. So they were pretty happy with the 12-inch joint. This was the first tier of the press box. So the press box was fabricated in Stockton. It was actually all put together in Stockton in 5 sections and then taken apart. And trucked into the stadium through that North Memorial Arch, and then reassembled to make sure that it all still fit. And then they brought in this yellow crane. This yellow crane was used to assemble this crane. This crane was brought in on 72 flatbed trucks, assembled in place. And then it, in turn, picked up each of these 5 segments of the lower tier of the press box. Again, here the span looks like it's more longitudinal, but we actually designed these as space frames with a transverse orientation because we knew that they were going to be picking these up in sections. Probably, if it was shored, which it really couldn't be because that wouldn't have allowed us to build the stadium bowl in advance. But this very much affected even our steel detailing. along the way. Here's a photograph of the installed viscous dampers that were in the stadium. This is a finished photo of the high performance student athlete center in the foreground and the stadium in the background, and you can see the press box kind of looming on top. There's a photograph from the stadium floor looking back up to the press box. The architects were actually trying to, you know, in preservation architecture, they actually liked the idea of the press box looking very modern, and they kind of wanted it to look like it was floating above the stadium, which was why it was supported on the 4 cores, and you can see air going through it. It caused us more than a few design headaches, but I think they achieved aesthetically what they were looking for. And last but not least, it's back to my timeline. At the bottom, I put on both my professional activities and civic community activities. You know, I highly recommend that, you know, whether you're in academia, whether you're in professional practice, get involved in these organizations. One, you meet the nicest people, but you also learn a lot about teamwork, about, you know, what people are trying to do. In my case, it was really EERI that I did the heavy dive in, but I also got involved in kind of civic community activities, and even with joining the board, you'll see very much at the bottom, Build Change, Geohazards International, the U.S. Resilience Council. I've become more and more working on policy and advocacy about worldwide seismic resistance, and that's kind of the stuff that keeps me turned on. So I think I tried to do this in an hour, and I think I'm almost there, but I hope you have some questions for me. I wanted to leave some time to allow for questions.
Awesome. Thank you, David. Yeah,
Thank you,
like I
David.
said, we are open to questions now. So if you want to go ahead and unmute yourselves, or just type it in the chat box and we can relay it.
Great. I had a few. So going back to your first project, I have minimal experience with the Friction Pendulum Isolators, and I was hoping you could speak to the other 2 forms of those isolators and, you know, the pros and cons of choosing one versus the other.
You know, I mean, it's a good question. You know, a number of my early base isolation projects, San Francisco City Hall, the base isolation retrofit of the Asian Art Museum, which was just a cross Civic Center project. These are public sector projects. And so we actually had to write a performance specification for the isolators, because they had to be competitively bid, you know, so we could not, you know, have a preference, even though the vendors love putting pressure on us, you know, but we have to be fair about, for the client's sake, for, you know, price competition in a public sector. So we had to think about that a little bit as well, you know, in terms of the cruciform floor design, the elastomeric isolators. So your question was about, you know, the elastomeric isolators are really like a layered birthday cake, because they're layers of rubber and steel vulcanized together, kind of baked together. And so we write the specification in terms of what sort of drift, what sort of, you know, kind of energy dissipation had to be written into it. The friction pendulum, operates on the friction between steel surfaces, and that the ball bearing and the convex steel surface, that it's rolling up and down. And I think I had a picture of their later innovations where it's a pendulum within a pendulum. And what's good about them is I mean, they also have a very small profile. So there's a lot of advantages to each. The one thing I would say, and this was more early on than necessarily today, is the elastomeric isolator had a better resistance to uplift than the friction pendulum did. And in the case of San Francisco City Hall, those light court walls came down, and we extended them on at the ground floor to longer outrigger walls, so that there was very, very little net uplift on those. Does that help?
Yes, thank you.
We had another question, and it pertains to base isolators. The question was, what would cause the base isolator to fail in an earthquake, and is there a type of shaking that would make them not work properly?
So it's a very good question. Honestly, I could have talked about that for 2 hours on my own. And the other thing that's kind of interesting was, we were doing the base isolation retrofit of City Hall before base isolation was in the code. And there was a good and there was a bad part of that. But we of course thought about those things. So one of the things is we designed the isolators for the design basis earthquake, for the displacement that we would get in the isolators for that earthquake. Every isolator got tested, for that displacement. I mean, they're produced, but we also designed the isolators for the maximum credible earthquake to remain stable in a maximum credible earthquake excursion. And we expected that excursion to be 28 inches. And so the moat walls around the building are 30 inches. What we feared is that how they could fail is if they go beyond their ability to deform laterally, could they roll over? And then you maybe lose the vertical support. We debated, and there are some projects we've done, actually new buildings, where instead we design a steel catchment. So let it roll over, but it's only going to fall 1/4 of an inch onto a steel catchment. I have photographs of those kinds of things. The other thing about kind of the testing, one of the concerns about an elastomeric isolator, rubber, is that can rubber over time become brittle? Now the metallurgy or the chemistry of the high damping rubbers is they feel that over time they don't feel that it will embrittle itself. They don't think that would be the case, but that's why the code now requires in any base isolated building, you have to have the ability to go in, take an isolator out, take it to University of Nevada, Reno, or someplace where there's a testing lab and test the isolator. With the friction pendulum, the concern is steel on steel welding, just over gravity load over time. Now, again, they feel that that's not the, that's not the concern. There is a little bit of what we call the stick slip event, that in the friction pendulum, you need enough of an earthquake to get the friction pendulum going, and up until that point, it's kind of responding like a fixed base building. But these are things that engineering designers are thinking about. We're still waiting in the U.S. for a real test of these isolators. Most base isolated buildings are instrumented. Most have this capacity, all have the capacity to take them out and test them. After an earthquake, you have to be able to go in and inspect them and make sure that they have remained elastic, that there isn't now a new permanent deformation in them. But that's the failure mechanism that we worry about, and that we design for.
Awesome. One more question on base isolations. Can base isolators be placed on any building, or are there specific structures that you recommend them over others?
So I cut my teeth in base isolation doing historic building retrofits. And as I mentioned, in the case of San Francisco City Hall, the jewel we were protecting was the dome. I think it's really suitable for historic buildings that have brittle, archaic materials in them. Because you can retrofit it with being less intrusive to the rest of the historic character of the building. You still have to be able to get the isolators in, and in some cases, there are physical limitations where that may not be the solution. Another limitation of base isolation was that period shift issue. So you don't want to base isolate a building that has a 2.5 second period, because then you're going to get harmonic resonance. So there's a practical height limitation, because of what the fundamental period of the building was going to be. You can't really base isolate a high-rise building. I would say you probably can't base isolate a building much taller than 15 or 16 stories. We weren't the engineers of record for LA City Hall, but that's a pretty tall building, and I would have been a little nervous about that if I was the engineer of record. But of course, I'm sure they dealt with that. That was designed by Nabi Youssef, LA office. I happen to be a big believer in base isolation. I think it is the best anti-seismic system we know of, the best high performance system we know of, which is why most hospitals in California today are base isolated.
I got one more question on base isolation for you from the chat. So they're called base isolators, but could you apply base isolation to a specific story and not the entire building?
Oh yeah. Oh, I mean, basically the base isolators in most cases are only in one plane of the building. They're only in, in the case of City Hall, it's, we actually created a new floor. If you talk about the premium cost was getting them in, but we basically had to create a new first floor. And that's even true on new base isolated buildings. You have a foundation system, usually, your first floor is a slab on grade. In this case, that's the base of the isolation plane, and then you have to build the floor on top of it. We did one building where the isolation plane was at the top of the first story. So it was on column and column capitals. But you have to remember that anything that crosses that isolation plane has to be able to handle the 30, 36 inches, 48 inches, whatever the design movement of the isolators is going to be. You know, everything that traverses that has to withstand that motion. So any sort of electrical or plumbing conduit has to be in flex connectors and be able to handle that kind of motion. In most base isolated buildings, the elevator pits are suspended by the floor below. And so you can picture the elevator pit is a pit within a pit, you know, so that it's moving around within the pit. So you really don't want anything that is impinging on the isolated motion of the building.
Awesome. Was there any more questions? Anybody have anything else they'd like to ask?
Yeah, I had another one. What type of framing was used in the dome of that first project?
Oh, for any of you who are students of historic architecture, it was a Brunelleschi type of dome. It was a dome within a dome. So it was steel with radial steel beams, you know, and beams in between. Infilled between the beams was sandwiched a very brittle terracotta. There's then an inner dome. And if any of you have, you know, ever come to San Francisco, come in and walk into this building. It is really a magnificent building. And you can, I don't know if you can see isolators, but you can certainly see the moat. You can see the cover plates. You can see a lot of aspects of this. But the inner dome is also a steel, you know, radial beams and transverse members. What's interesting is the inner dome, which is plaster, is suspended from the steel grillage, and what they use to suspend the lath of the plaster was horsehair embedded with plaster of Paris, and we actually tested all of that. And decided to leave it all in place. So still to this day, the inner dome is suspended by horsehair and plaster of Paris.
Very cool. Thank you.
We have a question from one of our professors. He said, would you speak to what type of education students should seek if they want to do the design of larger and more complex structures?
I may give you a controversial answer here. And I mean absolutely no disrespect to the curriculum that students are getting, whether it be undergraduate or graduate. I think you're getting enough. Honestly, if you want to design big complicated buildings, really what I hired for when I was doing the hiring, what the firm still hires for today is just smart people who want to learn. There's a large amount we can teach you, so I mean, you can take courses on base isolation, to understand the principles, dynamics and stuff like that. I mean, I've often gotten the question from people as to, like, I'm in my graduate year and I have one class left. I've met all of the requirements. I've read all of the engineering elective requirements, but I have one more course. What should I take it in? And I say, comparative literature, history of architecture, I honestly, I like engineers who are broad thinking, well-rounded, and who can think. So I'm sure where you are, you're getting great courses, and you should take dynamics courses and properties of materials and all sorts of dynamics, but just get ready that when you go into practice, just be a sponge, because you're going to be learning a lot, and we take it on ourselves to help train you and expose you. And by the way, and it's not just for LLSS, it's every great engineering firm out there, is one of the things that we do is, if we have any expectations, it's to become licensed PEs and licensed SEs. And we're going to give you the experience to be able to pass those exams. That's our job. That's our goal. And so we actually train people that, no one in our firm just does analysis. No one in our firm just does concrete design or steel design. In a way, we're trying to train people to be jacks of all trades. Sure, we have some people who are specialists in certain areas, and that can be what they have focused in their undergraduate and graduate and postgraduate years. We're going to take advantage of that. But my simple answer to the question is, I'm always looking for breadth. I'm looking for people who are just good, well-rounded thinkers.
Awesome, thank you. Was there any other questions? Oh, there's one in the chat. Besides joining a club like ERI, what other advice do you have for students that will graduate soon? What's something that you wish you learned earlier in your career?
I think it's, it is to get involved in some professional society, and in something. And actually, it doesn't even have, you will, if you are working in the Bay Area, your employer is going to tell you you almost have to join the Structural Engineers Association of Northern California, or wherever you are. I always tell people join EERI, but I also think that if there's one of the nonprofits that I got involved with early on, and early on in your career, time is at a premium. You might have a young family. We all work to live. We don't live to work. But there is real value in kind of that which you do for your own kind of community growth. I joined a board of an organization called Asian Neighborhood Design, and it was a bunch of old hippie architects from UC Berkeley who wanted to do kind of community architecture. And I joined the board years after inception, where they were actually working on workforce development and training for low-income people and people of color. And I'm kind of a social justice guy stuck in an engineer's body, and and so I found that once I got involved with them, that just opened me up to a whole new world. And plus, you just met a lot of people doing different things. So I think my recommendation is just you're going to be busy as an engineer. There's be a lot of demands on you. You're going to be learning a lot, but see if you can, carve out a couple of hours a week or a month maybe to, work for a nonprofit, volunteer with a nonprofit, because I think it's just, it's rounding, and frankly, look for engineering firms that will encourage you to do that. Firms that, like our firm, gives people paid, 3-4 hours a month to go out and volunteer.
That's awesome. Is there any other questions anybody would like to ask?
I had one last question. Promise it's my last one. I was wondering what software you use to do the time history analysis on that San Francisco building.
I'm trying to think of what we used at the time. I think the model was done in SAP, if I'm not mistaken, but I'm not sure. I'm not sure. I'll get back to you. So there are a few facts that now escape my memory.
Anything else? All right. Well, I think that's it. We're pretty close to 6:30. So just wanted to thank you again, David, for coming. It
A
was
pleasure.
great pleasure. And thank you everybody else for coming as well.
Thanks very much. Have a good
Time,
evening.
David.
Thank you.
Thank you.
Thank you very much.
Thank you, David. Thank you, Jack.
Thanks, David.